Back in April 2026, a lot of us were bracing for Cyclone Vaianu. We were preparing for a major hit, but when it finally arrived, officials seemed, well, relieved. The storm just wasn't the monster everyone had feared. And the reason why is the whole point of this explainer. By the time Vaianu reached New Zealand, it wasn't actually a tropical cyclone anymore. But now think about Cyclone Gabrielle back in 2023. It also wasn't a true cyclone when it hit our shores, and yet it became our deadliest storm since 1968 and the costliest in the history of the entire southern hemisphere.
So that raises a huge question, right? If these things aren't technically cyclones when they get here, then what are they? And how on earth can they still be so incredibly destructive? Okay, let's get into it.
To really understand what happens, we first have to look at the blueprint for a perfect, honest-to-goodness tropical cyclone. The best way to think about it is like a giant, perfectly oiled heat engine.
These storms need very specific conditions to be born. They form over these huge stretches of really warm ocean water. We're talking at least 26.5 degrees Celsius. All that warm, moist air rises up, and that creates this powerful spinning system. And here in the southern hemisphere, that spin is always clockwise, thanks to the Earth's rotation. It's a little thing called the Coriolis effect. Just imagine a perfectly balanced, fast-spinning top. It's incredibly powerful, and it just keeps going, as long as it has that warm ocean energy to feed on. But as that storm starts its long trip from the warm tropics down towards New Zealand, it has to run a gauntlet. It faces the series of challenges that don't just weaken it, they completely change its DNA. So as it heads south, it runs into three huge problems that start to transform it. First, energy loss. The storm is moving over colder and colder water, basically losing its fuel. Second, disruption. It hits these powerful, competing winds at different heights. That's called wind shear, and they start to tear it apart. And finally, that leads to a total collapse of its structure, where the beautiful, symmetrical storm we all recognize just breaks down. See, that 26.5-degree water is absolutely critical. As the storm gets closer to New Zealand, the sea temperature just plummets. The high-octane fuel for its engine is suddenly gone. But losing its power source, that's only the first part of the problem. Next, the storm slams into its second major challenge, wind shear. You can think of it as strong competing winds blowing at different levels of the atmosphere, and they literally start to rip the storm's structure apart. Remember that spinning top? Well, losing the warm water makes it slow down, and then the wind shear comes along and gives it a huge shove, making it wobble like crazy and pushing the top of the storm clean away from its base. This 1-2 punch causes the cyclone's organized, tight structure to completely fall apart. That famous calm eye just collapses. Now, the scientific name for this whole process is extratropical transition. And the most important thing to get here is that the storm isn't just weakening, it is becoming a completely different type of weather system. So here's the crucial bit. It changes its engine. A tropical cyclone has what's called a warm core. It's sucking up all its heat from the ocean. But an ex-tropical cyclone, it develops a cold core. It's now getting its power from a totally different source, the massive clash between the warm, tropical air it's dragging along with it and the cold, polar air that we have down in our part of the world. This new fuel source is what makes its structure so messy and sprawling. All right, so let's tie all this science back to the real-world storms we started with, Vaianu and Gabrielle. Both of them went through this exact same transformation process. For Vaianu, this extratropical transition ended up creating a much weaker, more manageable storm by the time it reached us. That's one possible outcome, and frankly, it's the one we're always hoping for. But with Gabrielle, the story was tragically different. The transformation didn't weaken it. It basically re-engineered it into a new kind of monster. And let's be absolutely clear about this. The storm that caused all that devastation, Cyclone Gabrielle, was an ex-tropical cyclone when it hit New Zealand. Its new, sprawling, messy structure ended up interacting with other weather systems over the Tasman Sea. This allowed it to just scoop up unbelievable amounts of moisture and dump historic levels of rain. We're talking 300 to 400 millimeters in some areas, all while producing incredibly powerful winds. The transformation didn't make it weaker. It just rearmed it with a completely different set of weapons. The result was just catastrophic. The estimated damage was 14.5 billion New Zealand dollars. That made it the single most expensive storm in the history of the Southern Hemisphere. And tragically, it was directly responsible for the deaths of 11 people. So what's the big takeaway from all of this?
Well, it really boils down to New Zealand's unique place on the globe. Our geography is the exact reason we so rarely, if ever, get a direct hit from a true, intact tropical cyclone. We're just too far south. The ocean around us is too cold, and our little corner of the world sits right in a zone of high wind shear. It's the perfect cocktail of conditions to force that transformation. So there are two huge things to remember. First, the intense storms we call cyclones aren't technically tropical cyclones by the time they reach our shores. But second, and this is the most important point of all, that transformation does not automatically make them safe. An ex-tropical cyclone is a different beast, not a lesser one. And this really sums it all up perfectly. New Zealand's geography doesn't act like a shield that stops cyclones. It's more like a workshop that transforms them. And as Cyclone Gabrielle taught us all, what's left after that transformation can still hit very, very hard.